Good afternoon. It is an honor, it's a real honor to be at this extraordinary event today. And now, as we are nearing its end, I would like to pull some of the common strings together. I want to tell you about a transformational, truly transformational game changer in science. One which is happening just right now in the front of us, of our eyes, and one which makes me have something new to say almost every month. I feel as if I'm in a kind of magic reality. Something which looked like magic just a few years ago is becoming reality, and this new reality is revealing new magic. What I want to tell you about today is a search. It is the search for life on other planets, for life outside of Earth. This is a search which takes us very far and also close to home. When it takes us close to home, one of the places which we used to dream about and now we search actively for life on is our neighboring planet, planet Mars. This is in front of you an image of a landscape from Mars just from 2 months ago. It was taken by the Curiosity rover, and it is a beautiful and eerily familiar landscape. It's also tantalizing, because it seems that finally we are seeing the geological record of planet Mars, the full history imprinted in its rocks. And we have a chance, and we are going to try to find out whether in the past history of young planet Mars, there were any traces of life, or maybe even still traces of life on our neighbor planet. If there was life, then we would like to know whether it's similar to that here on Earth. We would like to know why it never flourished like life on Earth did. But most of all, just look at it, at this iconic image. Wouldn't you like to be there? Right there? I would. In fact, I would venture a prediction today. I would predict that today in this hall, there is at least one of us, somewhere here, who within our lifetimes will be standing just there in person and looking at this same landscape. So that's what we do to search for life near us. Today, Mars is a desert. But if we take Earth as an example of what happens with life, a global, long-lasting biosphere encompassing the whole planet, then we should be looking for life not just near to home, but very far away too, to other solar systems, to other stars with Earth-like planets. And today I want to tell you that we are doing this. And the way in which we are doing this is to first, as a first step, try to answer the question, how common are planets like the Earth around other stars? This is the main goal of a project, the NASA Kepler mission, which I'm proud and really happy to be part of. 12 years ago, I was part of the team which put together the proposal for it, and now we are running it. This is a space telescope which is using the so-called method of transits to detect planets around other stars. When they pass in front of their stars, they dim just slightly the light from those stars, and they do that periodically if their orbits are inclined just in the direction facing towards us. And with this Kepler telescope, we already have discovered more than 3,000 candidate planets. Many of them are of the same size as the Earth, and this gives us an opportunity to estimate how common such planets are. It's been already 3 years, and we need another 3 years to give the precise answer, but we already know that those planets are out there, and in fact, there are very many of them. And this gives us an opportunity to, first and foremost, say, what is the estimate of such planets, like the Earth in their habitable zones, that we expect in our galaxy alone? And that estimate, total for our galaxy, comes out to something of the order of 200 million habitable planets. This is a large number, but what is most exciting about it, this allows us to go to the next step. And that next step is to find the ones that are near to us. You see, Kepler, in order to determine the statistical number, the frequency of such planets, is looking in a pencil beam far into the galaxy, about 1,000 to 3,000 light years away. And yes, we are discovering those planets which can study them, but to truly study them carefully, to be able to look for the faint signatures of a biosphere, we need to do the next step. And the next step is really to find the nearby ones. Now we are getting ready to start that search, and that search will look closer to us, to the sun. And because of Kepler, now we know that we'll be able to discover about, or at least about 300 such planets. Planets which are roughly the size of the Earth, all the way up to about 2 times larger than the Earth. We call those planets super-Earths because they're larger than the Earth. But as far as we can tell, there's good for life and for what we expect good habitable conditions to be as our own planet. And most importantly, there are many of them. We can study them fairly easily. And this is where we are going next, to do that. And so in that family of super-Earths, of which our own Earth is just one member, and you've probably heard about one which was announced just earlier this week while we were all here a couple of days ago, which is one of those bigger ones in that family. That is where we hope to focus our search and discover some signatures of life. So the question then, in summary, is now that we know the basic fact that Earth is just one of a multitude of such planets, what about life? What can we do in order to understand both its true nature and also how to find it? Is there life on other planets? That's the big next question. And immediately I want to tell you that when I say life, I really mean all of it, the entire biosphere as we know it, and more precisely, the distinct chemistry which defines it. That's why I equate life on Earth as biochemistry, that basic chemistry. And then the question is, well, if it's so difficult to find life on Mars, how do you even hope to find life on other planets which you can't get to? And the answer to that is, yes, we are going to try on Mars. Maybe we will find something there, and to us scientists, finding just one more example will be crucial to understand the true nature of what life is. But as I said before, we have to go beyond the solar system because that's where we will find the conditions which are truly different from those of Earth and understand both the question whether there is life on other planets and also its nature. And the big question is, how do we do that? Well, in the past many years, we've actually learned some basic things about life. And one of them is that life produces byproducts which it emits into the atmosphere out of its activity. And if these byproducts, for example, gases which can dissipate and accumulate, even in small amounts in the atmosphere of a planet, we know nowadays with the techniques of remote sensing how to detect them. And there is a good example here, a very common cyanobacterial life on Earth, the green mat, the beautiful green color there, which is constantly producing oxygen gas as a result of its activity. So we're trying to see the little bacteria there, the green stuff, and the way we can detect it is through the silver little bubble, which is the oxygen gas that it produces. But the really difficult question, the one which is both fundamental and very difficult, is what if the chemistry of that other life is fundamentally different? In fact, it will be silly to assume otherwise, wouldn't it? That all life around there is just carbon copies of what we have here on Earth. And we will be really unable to discover it if we don't know what we are searching for. And this is the next big frontier, is to really understand what is the possibility for alternative biochemistries there. Fortunately, this is something which we know how to do. We know how to do it in our own labs. And this is where science is now going in a big way, trying to understand, is DNA the only molecules which can be used to carry genetic information? Are the metabolic cycles which take sunlight and produce oxygen out of this, or methane, like in the case that you see in front of you now? Are these the only possible metabolic cycles? What are the possibilities? And then astronomers like me take the information from those labs in the biologists and look for those signatures out there. And then we come to the ultimate question: are we alone? If life happened here on our planet with relative ease for 4 billion years and eventually developed to the complexity to which we see it today, and the ability to have the technology to communicate across the distances of the galaxy, which is what we are, then where are they? Where are the others? This is what is known as the seeming paradox for about 60 years now, called quite often the Fermi paradox. And I want to give you a short history of the universe which gives a different perspective to that, which may be one of the many possible answers of why we haven't seen any other advanced civilizations out there. And that is the brief history of our universe as we understood it in the last few years, literally. We are now able, if we start from the time today, to go back in time and see that green, yellow, blue image, which is actually the image of our early universe, a warm, hot gas of hydrogen and helium alone, without any stars, without any galaxies, which we call the cosmic microwave background last scattering. And from there on, we see how stars are formed, we see how planets come to be, and that's all happened in the last 13.5 billion years. And in fact, the planets that are rocky, that have the heavy elements, only happened around those stars in the last 8 billion years. So if we look at that, then we realize that even if we are not the first life in our galaxy, we certainly are of the first generation. And this is like we think anthropomorphically about generations, not necessarily all born at the same year, at the same month, but that have a common peer group, something in common. And what we have in common is that we all come from the chemistry of our planets. We are like parent and offspring. And then we can imagine the second generation, the one which is coming after us, a tree of life that is not anymore, is no longer rooted in the chemistry of the planet. In fact, a tree of life which is begotten by another tree of life, a kind of an exponential chain reaction in this galaxy, which is probably just starting. And Craig Venter talked about that as glimmers of what it could be in terms of the synthetic life that comes by. And this brings me to the way in which I want to finish this, which the famous science fiction writer and scientist Arthur C. Clarke said in a very interesting, maybe messianic way about how he imagined the distant future of the universe and life and civilizations in that distant future of a universe which is quite similar to what we have today. But very far in the future, we know that the universe will go for much longer than it has gone so far, and those civilizations will have knowledge and power that we can't imagine. And he said, but despite all this knowledge and power, they will envy us because we knew the universe when it was young. I'm proud to be of this first generation. We are the pioneers. You are the pioneers. And we should live our lives as ones. Thank you.
Wow.